Okay, hi student and audience. This is the first lecture on this topic. In the previous lecture, we went through all the practical details about the optocoupler and operational transconductance amplifier TL421. Okay, so in this lecture, we'll discuss how to design or build the two-pole 1-0 compensation using those two components. So first, let me review the basic things about our converter. So you have a converter, flyback converter, and this part belongs to the NCP IC made from on-semi conductor. I think once I told you that is from the Infineon. It's not from Infineon. It's from the on semiconductor, and the device name is NCP1230. Okay, so this is the inside of some error. So the bias voltage is provided from this flyback transformer with one auxiliary winding. We will go through the details about that. So this thing is fixed. And this is the optocoupler. Two important parameters is CTR, current transfer ratio, and the value of this parasitic resistance CJ. Okay, and this is TL421 operational transconductance amplifier. Okay, and let me review this. This is the full schematic of this TL431. So this is the anode, which is ground, and this is reference, which is non-inverting port, and this is inverting terminal. But inverting terminal is inside of this chip. Usually, the operational amplifier has this symbol, and the inverting terminal is here, and the non-inverting terminal is here in the output, and there is the bias terminal. Okay, this is the conventional operational amplifier notation, but somehow this one of this, actually this here, later on we will swap the polarity of this. This is inside of this is built in. Okay, so you cannot access this, and only you can access this terminal. Okay, and this there is no energy source here, so the external bias circuit should provide IK DC voltage at DC current DC current at fixed this voltage, and this one should be sufficiently larger than 1 milliamp, and this VK should be sufficiently larger than 2.5 volt, which is same as this reference voltage, and this is specially designed reference voltage. So you can assume the one voltage source is internally connected to this inverting terminal, right? And this is the differential pair. So you are learning this from the electronics course, probably electronics 2. So you know the operation of this. Okay, and this is compensation cap, and this the green curve is this one is bias circuit. This is input, and this is also bias circuit, and this is called the connection, cascade connection of two transistors is called Darlington pair. Okay, so this functions as the inverting something. So the polarity will be changed because of this. So the symbol is this one. This is the symbol of my creation. So this represents the functional behavior of this. This is swapped horizontally. Okay, and this cathode reference, like this reference and this reference are different. Okay, very confusing but different thing. This is non-inverting terminal, but later on it becomes inverting terminal. and this is notation of this inversion function. It's not an inverter, okay? I said if this voltage is increased, then this voltage will be decreased. If this voltage is reduced, then this will be increased like that. So the inversion functionality is built in here. So I'm using this symbol with this inversion, then polarity of these two terminals will be swapped. So we have this, then this is the same as the operational amplifier symbol, okay? And this is simplified to this because the presence of this reference voltage, so very strange symbol, and some people, they think there is the genodiode, which is the true for one special connection, okay? But usually this is the correct notation of this TL431 operational transconductance amplifier, okay? Okay, and we went through this actually. So basic optocoupler isolate compensation. So we have this configuration. This is the simplified version. Later on, I'll show some details about this. But this is the basic structure, and this is called common emitter configuration. So it has some limitation, and maybe there are some other common collector configuration that has the limitation, but this is the more popular. Maybe this emitter is grounded, so they call it common emitter configuration. Okay, and this is the feedback circuit, and the feedback mechanism is built in here. Suppose this VO is increased, then this minus sign means this is negative feedback. This is reduced, then ID will be increased because this is reduced and this is increased, then ID will be increased, then IT will increase. Okay, there is a constant in between, and then this increase, then voltage drop will increase, then voltage level will be decreased, then this PWM, the width of the PWM signal will be reduced, D will be reduced, then output voltage goes down. So if something happens, something went wrong, there is a mechanism to fix this. Okay, that is the basic principle of negative feedback, and we will analyze this. Then we will find the transfer function of this. This negative is coming from this, and this is the input, and this is the output. Then transfer function is this form. So this is the integration, and integrator gain is KB, and we have 0 at low frequency, and we have 4 at high frequency, and the parameter of this KB and omega GC, omega PC is given by here. We will derive this, and the problem becomes obvious because this CTR and this CJ are coming from the optocoupler. So maybe there is some unknowns, uncertainty, some tolerance because of the exact information of optocoupler is usually not provided. Okay, that is the one problem. And this RT is inside of the IC you're going to use, so you cannot change it. This is fixed. And RD has some limited range to provide sufficient ID, bias current, and bias voltage. Okay, so there is some limitation. That is the price we are paying because in this IC this is fixed. Okay, so there is some limitation, but that one caused the big problem here. Okay, all right. Detailed analysis of this is shown here. Okay, so very similar to the previous case, but this part is modified. So there are 3 resistance, but it looks complicated, but it simply works as the voltage divider, actually. Okay, so there are many voltage divider here. So this looks complicated. Most of them is just current divider or voltage divider. Okay, so extremely simple. Looks scary, but It's a very simple one. Okay, and then we needed to find out our object is to find transfer function from here to there. Okay, so complicated. So we have divide. Okay, let's call it FVS, and we have negative sign in front of this because there is a negative feedback mechanism built in here. Okay, and we divide 3 transfer functions. So this is the input, this is the final output. But first, consider this transfer function from here to there, and the transfer function from here to there, and the transfer function from here to there. Okay, 3 cascaded transfer functions. So we have this, and the first one, the transfer function from here to there is very easy because this is the VO and this is a non-inverting amplifier. So output is VO times G2 divided by G1 with negative sign. Okay, so it's shown here. Then this is a VO and this VX is this one. Okay, then current is the division of this voltage difference by this impedance GD. Right? So you have VO here. Then this can be rearranged like this. So we have this one expression. So we resolved this, and this quantity is voltage here. Okay. Second one is extremely easy. The transfer function ID from ID to IT is defined as CTR, current transfer ratio. So this is a CTR. Okay. Then transfer function from IT to VCon is even simpler because this functions as the current source. So you have current source here, and this is the CJ, parasitic capacitance of this optocoupler, and this is R2 and R1. They are in series, and the VCon is except in the middle, and RT. This port is grounded in AC. Okay, there is a DC fixed value. That means in terms of AC, it's grounded. So this is the circuit. Then IT is coming down. Then you evaluate the voltage of this, and that voltage will be divided by this R1 and R2. Okay. So this is the impedance. This one, parallel combination of 3 branches times IT. IT is voltage across this, and finally this is just a simple voltage division. Okay. So this is nothing. Okay. Then this is simplified to this. Okay. The negative mechanism that is also VO increase, VX decrease, then ID increase, IT increase, then this VCon decrease. Okay. The mechanism is the same as the previous case. Okay. But with this configuration, maybe we have some flexibility in selecting device, okay, but still there is some distraction because of this, right? So this is nothing, right? Okay, so then the overall transfer function from this out voltage, this control voltage is just the multiplication of 3 transfer functions you evaluate in the previous lecture slide. So that is shown here. Looks complicated, but somehow I divided it into 2 parts. This one is easy. This one is already factorized. Okay, and this one is actually this is a constant, and this will create the pole and 0. Pole and 0, right? This one is pole, so we know the expression of the pole, and this one create the integrator gain combined with this, and there is a 1 0 here. Okay, so we are using the general notation of G1 and G2 and GD, but in our case, this one is simple resistor RD. This one is RC1 and CC1. Okay, so we have 2 RD, not RC. So we have two resistors and one capacitor here. Okay, that simplifies our job. So use this notation A and B. Okay, first take care of A. A is this one. Okay, and actually this is the RD and CC1 and RC1. Then this GD is RD1 and this is the RC1 and this is the CC1. This is impedance divided by RC1 here. Okay. Then you factorize out this. Then you have this. This is what? This is 0. And this part becomes the integration. But you have additional gain here. So this part is, this is A. And this part is B part is coming here. This, no, this part. Oh, okay, I went too far. This is A part and B part. Is this one. This one is B. This is a constant. Okay. So this is B and we have another constant. And this is the integration gain and everything combined all together is integrated gain. So KB integrated gain determines loop gain crossover frequency of your converter. Okay. So eventually this one will determine the crossover frequency of converter loop gain, and this is the omega GC. Okay, so omega GC is fixed, but it comes at lower frequency. It comes earlier, and this omega PC is usually will be located, should be located at the frequency minimum of 3 candidate. This is RHP 0. Okay, omega RHP of flyback converter and ESR 0 of flyback converter, and have the switching frequency. Omega S is the switching frequency of this converter. So this should be placed the minimum of these 3 frequencies. Okay. But it's not easy to locate this because this is determined by this one. Many things are already fixed and there is uncertainty here. But you should use your engineering judgment in selecting this, or you need to fine tune in the final stage of your design. Okay, so this becomes 2-pole 1-0 compensation. Never call it type 2. Okay, 2-pole 1-0 compensation. Some case, I don't know which case, they need 3-pole 2-0 compensation called type 3. Okay, don't use that word. 3-pole 2-0 compensation. Then this one is very easy. You add this branch. Okay, previously there was only one resistor. Now you add this, and this one create pole and 0. Okay, this RD is coming in the denominator in the equation. GD is coming in the denominator. That means pole at GD becomes 0 because it is located in the denominator, and the 0 frequency becomes pole frequency because it comes in the denominator. Okay, so from this structure, there is a 0 determined by this product of this, and there should be a pole determined by product of this, and plus of this one and this one. You can easily verify that. Okay, so with this, there are additional 0 at this one, and this becomes pole, additional pole. So omega PC prime. Okay, so at the same frequency, it becomes pole. Okay, because this GD comes in denominator, so this becomes eventually, this is the pole in the compensation, and there is a pole frequency is originally determined. This one CC2 times RD plus RC2. Okay, just there is a loop here. Okay, from loop this is determined. You can easily verify this. Then this becomes omega GC prime. Okay, so with this, the transfer function is this one. 1, 2, 3 poles, 2 zeros, and the pole frequency is this one, and zero frequency is this one. Okay. Right. So this is the case of 3-pole-2-0 compensation, and this might be necessary for the buck converter, isolated buck converter with voltage mode control. But for the current mode control is used, you don't need this. Okay. Simple, but knowing this will simplify your job. Okay. I think I explained this several times. And peak current mode control. Peak current mode control is the peak value of inductor current. Magnetizing inductor current is sampled by sensing the switch current, and that information is mixed with compensation lamp and compared with the control voltage to generate PWM waveform. That is this one. So we have this. Originally we have VI. VI is output of this current sensing network. So it senses the switch current, and the switch current is on-time inductor current. I'm talking about the magnetizing inductor current. So magnetizing inductor current is this one, continuous triangular waveforms. So we are only extracting the on-time part of it, which is switch current. Okay, and that is multiplied by this gain, CSN gain, and that is this one, VI. VI is fixed, V minus here. Okay, this is VI, and it is added with this lamp signal. Then the resulting signal is V minus, indicating the voltage at the inverting terminal of PWM modulator. That is shown here. This is the lamp signal, and this is VI. They are added together to generate this V minus. Okay, V minus is this one. So let me use black one. So this is this, and the same thing. Okay, this is V minus. Okay, when this intersect with this V cone, this QT is a switch drive signal. It was high and it becomes low, and something like this. Okay, that is the basic principle of peak current mode control for any PWM converter. Okay, this is enough to understand, to explain or design or analyze the peak current mode control. Okay, why this is necessary is something else. Then you need to go back to the previous lecture slide. Okay, there are good reasons. It has some history to use this. Okay. So anyway, this is the final result. So this is the PWM waveforms associated with this PWM block and the current sensing network and the V lamp. This is called compensation lamp with some reason. Okay, very good reason. You may figure out that. Okay, if you go to the previous lecture slide, and this is the schematic, full schematic of our prototype converter. Okay, some engineer, I think they used the tool, PCB making tool. Okay, so this is the transformer, flyback transformer. This is a magnetized inductance. Right. So this flyback converter is derived from buck converter combined with boost converter. So if you take a look at this converter, it behaves as the buck converter. Okay. Actually, this inductor is here. Magnetizing inductor is here. Okay. So if during on time period there is no current, then inductor can be moved here. Okay. And during uptime period, this is connected to this port. Assume this is the 1-to-1 transformer, then it is same as the output part of boost converter. So there is a filter here for the buck converter. This filter structure is obvious because we have L here and we have this output capacitor and the load here. This is split, okay? Because this is a low pass filter, but boost and buck boost converter, inverter, inductor is coming in the front part of this something. And there is just some transformer here, flyback transformer or something, okay? So this is the average model of boost converter, okay? So where is the low pass filter? Low pass filter is still here, okay? This will be reflected to here. And because you have transformer in between, maybe this L will be changed to something, okay? Divided by D prime squared, something like that. But still we have LCR low pass filter, okay? So same structure, so it's not easy to understand the operation of this, okay? Buck converter is so obvious, so natural, okay? You don't need anything, but boost converter is something different. Buck boost converter is different, so you follow the flow, okay? Then you can understand this, okay? The reason I'm saying this is, last time we talk about the two-stage filter, that then already the L is here in the form of Lm, and there are some transformer, so Lm prime is reflected like this, so Lm prime is here, okay? And if we understand the operation of this is just so obvious. This inductor is working, magnetizing inductor is functioning as the regular inductor in other converters, okay? So consider L is here, C is here. This is the single stage filter. Then if you may want add some additional stage to make two-stage filter to knock out the high frequency noise and ripple component effectively, I suggest you add one small inductor here and small capacitor here. Okay, so big capacitor, original capacitor is this place, and you add some small capacitor. Big inductor is here, and you add small this inductor, plastic inductor or something. Okay, this is the two-stage filter configuration, right? The region so this is the original flyback capacitor. This is large. The region placing here is there is some additional parasitic capacitance coming in this part. Then that will be merged, smeared into this large capacitor. If you change order of this capacitor, then the parasitic capacitance will influence this much. Okay, so this is a smart choice. Transfer function remains the same. I told you the transfer function, the order of this device is totally independent from the transfer function. Okay, transfer function is not determined by this order of their appearance. Is something else. Okay, so that's one thing I'd like to mention here. So this is the first one, and another one is this one is for the measurement of the control to output transfer function. So you can ignore this. You don't need this. Okay, and this can be connected. Okay, during the normal operation, but with some capacitor, small capacitor value. Okay. Okay. Let me explain something about this. If DC is connected here, still you can use this converter. Okay, but this is isolated. You directly connect this, right? Because there is no chance of electric shock. Electric shock is not coming from DC source here, okay? But for this offline converter, energy source is coming from the utility line outlet, AC outlet in your wall. and the energy they are coming is infinite energy. Okay, people can die if they got electric shock. Okay, to avoid that, this should be this part and this part should be perfectly isolated. Okay, if you see the two wires in the AC line, you touch this one, you got shocked. You touch the other one, you also shocked. Okay, so that is related with the ground. Okay, ground, the chassis ground. All right. So to avoid that, if this is the offline converter receiving the input from the utility line, this is the requirement. So there is isolation here, like this. Okay, this one works okay. Okay, but purpose of this is then there is just some EMI problem. Okay, so this is very small capacitor for the 60 hertz or 120 hertz AC. This is open circuit because the C is so small. Okay, but high frequency noise, even though C is very small, this is connected for the high frequency noise. Okay, which does not have much power. Then EMI problem will be reduced. You can overcome the EMI problem. So practically they are connecting this. Okay, and you just simulate this from PSIM. You don't need this. Okay, if you disconnect this, PSIM will complain you. Okay, PSIM does not know this. PSIM won't be shocked, electric shocked. Okay, so in PSIM everything is fine. Okay, but in reality, the safety of us, there is a requirement by law. So we should have perfect isolation here, here, and here. This one is okay because for the 60 or 100 hertz, it's isolated. But to resolve the EMI noise problem, some small capacitance can be used. Okay, when you are distinguishing between small and large capacitance, good value is 0.1 microfarad, 0.1 microfarad, or 0.01 microfarad is the borderline. Okay, beyond that you consider as a large capacitor, and maybe some nanofarad, picofarad can be considered small capacitor. Okay. Some student asked about this. He is not here, I think. Okay, so this is the second one, and another one is related with this. If you take a look at this is the main switch, and this is a current sensing network, and this is a gate drive circuit, and the gate drive circuit can be connected to the ground. Okay, can be connected to the ground. But if there is some circuit is embedded here, during this switching of the main MOSFET, turning on means you are charging this junction capacitor up to some value, high value, 15 volt, and the turning off means the discharging that capacitor. That current is, if this is directly connected to this, that will be sensed through this sensing resistor. Okay, that creates some noise problem, malfunction of your converter. So to avoid that, maybe this technique is just that part. It's circulating only this, and this will be the clean replica of the switch current. Okay, that's the reason why. I don't know the inside of this. I was thinking about this, but the only reason I'm thinking of is this one. Then this will be cleaner by putting this charging and discharging through this loop. Okay, I don't know. That is the reason I was thinking about this. Lesson 3. That is the reason I can think of. All right. Okay. And this one, NCP1230 from the ON Semiconductor company. This is called integrate current mode control chip. Okay. So inside of this, there is a ramp signal generated oscillator, and the ramp signal is, this is the ramp signal, and the current pass for this ramp signal is this one. It is generated here, and it goes to this. And there is some distance, okay, and here the switch current is sensed through this one. Here the switch current is something like this, and there is RS like this. This is R sense is here, okay. So this is just a simple voltage divider. This is a voltage divider, two resistance. Then the resulting compensation with the smaller peak value, that means increase the slope. Okay, the peak value is reduced, decrease the slope. Slope is decreased, so you can control the slope of this, and this one goes this positive terminal of this PWM comparator. Okay, and this part is coming from the Optocoupler. So there is some diode. Diode is connected. Let me use this color. Diode is connected here. This diode current, and this photo transistor is here and is connected here. And that voltage is, this current will be changed to the voltage. This is another voltage divider. Okay, just simply voltage divider, and that resulting signal is, where is it? It's coming here, sensed, and there is a main modulator, PWM modulator, and output of that is passing through this and coming out to here, and this is the switch drive signal. Okay, so this is a basic functional block diagram of. This is a way of understanding this, and there are some additional things, and there is something related with power factor collected rectifier circuit. This is not. This provide the, suppose there is one PFC stage in upstream, and this generates power. It power that chip. Okay, this is nothing, right? Okay, so this is the current mode controlled with the ramp compensation and direct port optocoupler connection. So this is the 8-pin IC, very handy, very easy to design, but they sacrifice the flexibility in design. They fixed many things, already fixed, okay? So they can reduce the number of pin. I told you this was very popular, still popular, okay? I was in Samsung Electronics, the power electronics division, and I was there as the manager of a system team. And at that time, maybe 30 years ago, at that time the MOSFET is here and the control chip is here. Okay, they are separated. That the one company, Top Switch. The company name is Top Switch, and the device name is also Top Switch. They merged this IC and the MOSFET switch, and they made 3-terminal device. Okay, so they use some cheap trick. Okay, and that was very sensational. Looks like MOSFET, but it has the PWM IC built in that Top Switch. Okay, so when I was working in Samsung Electronics, power electronic device, we are providing the ICs and the MOSFETs to Samsung Electronics. Okay, the consumer electronics department making TV and many home electronics. Okay, so they were using Samsung our MOSFET and our control chip, and they are considering to replace that with the Top Switch, because the Top Switch is very easy to use. Okay, can be miniaturize their product. So it was very urgent situation. So I proposed there should be some special process called smart power process, which can build the chip and the switch all together with the same process. That process was not here. Okay, so the way we selected, our team selected is we have MOSFET chip and we have IC and put them together in one package and put everything in TO3 package. Then it looks like this top switch. Okay, but problem with that is we cannot squeeze all the functions in 3 terminal environment. So we made 4-pin switch, Samsung smart switch. Okay, that is fine. Okay, they don't care 4-pin or 3-pin. Okay, so that guy, the top switch, they were so obsessed using only 3 terminal, something like the MOSFET. We used 4 terminal. Okay, there is no problem. Okay, so Samsung in Suwon. Okay, they are making all the home electronics. They used our chip. Okay, we are competing with our company. Our customer is Samsung Electronics, but Samsung Electronics is bidding from many companies, and they select the cheapest one, most cost-effective one. Okay, so they used our device, many millions of device. Okay, so I made some contribution there, and our team was very good. Then my boss still do everything. Okay, he said that is his work, something like that. So I was kicked out, and I went here. Okay, so I became the professor. Right? So I hate Samsung. I'm not using Samsung. Not any product. Samsung baseball team is my enemy. Okay. All right. That is the story related with this. Okay, squeezing everything. Right. Okay. Now I don't know how they are doing. Okay, but Samsung has all these ICs. Okay, comparable with this and competing with this. Okay. I hope they are doing well now. I combined the 2, this one and this one. So part of this is inside of this one. Okay. And this shows some details about the schematic or functional diagram of this NCP1230. This is just the magnified version of this, and I already explained this. Okay, so internally this lamp is generated like this, and lamp is coming out in this direction, and this is the current sensing current, and the switch current is sensed here, and the part of this lamp is coming here. Okay, so it is naturally mixed. Okay, I was thinking this is possible. This is possible. Think about the superposition principle. Okay, if there is no lamp, then there is this signal. Then this signal is gone, and only lamp is coming. Then you add them together. Okay, based on the superposition principle, then this will occur here naturally. All right, you don't need any adder or something. Okay, connect one node, common node. So this is the V lamp, and this is the switch current sensed signal, and some of them, and that is the compared with this control voltage, and this PWM block is generating pulse width modulate switch drive signal here. All right, and this is the soft start, some protection, something like that, and this is out of this one. Okay, so borderline of this NCP something is here. So this is this optocoupler photo transistor side. Okay, then this feedback signal is some voltage division, and the part of that is going through this, and compared with this, then this gate drive signal is generated. Okay, that goes in the gate, right? If you go to the IC company, you will be designing this kind of things. Then you should understand the operational principle of every converter, every PWM converter. Okay, without that knowledge, you cannot design this. Even the application engineer should know well about this, so they can promote the product. All right. So learning this basic thing is just not a matter of researching this area. Okay. So to have some sales engineer, you should know this. You should take my lecture. Okay. All of them. All right. So this is one example. Usually I'm not dealing with these details. This is nothing. This is not theoretical. There is no value, theoretical value, but very is some important, has some importance in practice. Okay. Then you can read the application note easily. You may find many mistakes in the application note, okay? But you should know this. And this slide shows how to evaluate the free lamp slope, okay? Or RI, current sensing network gain. There is also the voltage division and current division. So free lamp, internal free lamp is coming here. That voltage will be divided by this one, okay? So this is just the voltage division, right? But this one is very small. Then ignore this. Then this is the simplified equation. And the current sensing network gain, switch current is coming down here. And you think this is ground. You are applying the superposition again. Then current will be divided based on this and times this. So this is the part of switch current flowing through this R sense. So this is the voltage. That voltage is divided by this and this. So this is the voltage division. And with this assumption, R sense is very small. Otherwise, it's get hot. Okay, that is problem. Then this is the obviously satisfied. This is the simplified equation of effective lamp. Okay, so you should use this to calculate the slope of your lamp. And this is the RI, current sensing network gain. Not this simple resistor, very similar to that probably. I don't know. It depends on their value. So don't use this directly, can be different. So they are comparable. R lamp and R com can be comparable. Okay. So you need to know to this, right? And so we select these values or the compensation values. Okay. In the next lecture, 2 lectures, we will go through all the details, the procedure of determining these values to satisfy some requirement, okay, and how to determine. They are fixed, okay. You can select, you can change this and this, only 2 resistors, okay. That determines your performance of your converter, this converter. This is determined, assume this, they are determined, and then you need to select this, and this. And the final one is this one. This one is used to provide alternative current path for this bias current. Assume this is the 1 volt, then 1 over this is the additional current passing through this, and this resistance will be something similar to 50 ohm. So parallel combination of this is 50 ohm, so it won't affect this value much. Okay. So you need to determine this. And finally, the frequency of pole is selected, the minimum of 3 different frequencies. Okay, so this one is fixed. They are fixed. This one is measured. Okay, so there is no choice. Right? Then if the pole frequency calculated from your design is much higher than the one you selected as the minimum of 3 frequencies, what you want to do? You add external capacitor here, additional one here. Okay? So parallel combination of this and this is used to determine the pole frequency at the desired location. Okay? Same goal can be achieved by increasing these capacitance, these resistance, but they are fixed by this the NCP something. So you cannot change this. You should change this, and you need some additional capacitance. Okay, but you cannot reduce this. Okay, you cannot reduce this. You can increase. You can add something in parallel, but you cannot reduce this. So there is some limitation because of these values. Right? Okay. This is, I repeat these pages. Okay, that's all for today. So we stop earlier than usual, 50 minutes. Okay, next time we'll have extra 50 minutes to compensate this. All right? Okay, we stop here. Thank you.